Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 5 on multiplying polynomials. Now again, today's lesson is a review from things that you've done before, but primarily in Algebra 1, and you probably didn't see a lot of this last year in geometry. So let's take a look and jump right into it. All right, now polynomials. Polynomials, which we've seen already even in the first lesson that we did in Algebra 2, are expressions that consist of the addition and subtraction of terms whose exponents are all whole numbers. They are an extension simply of our base 10 number system. And I want to take a look at that in exercise number 1 because it's kind of cool. Exercise number 1. Given the polynomial 2x cubed plus 5x squared plus 3x plus 4, what is its value when x is equal to 10? How can you determine this without the use of your calculator? If you cannot, use your calculator to help and then explain why the answer turns out as it does. All right, well again, let's just talk polynomials, right? This is a polynomial because all of the terms have a variable that's raised to a whole number power. So we don't have any negative powers, we don't have any fractional powers. X to the third, x to the second, x to the first, right? And then our constant term added on the end. See if you can figure out, without your calculator, what the value of this polynomial is when x is equal to 10. And as a hint, I chose 10 for a very specific reason. Pause the video now and see if you can figure it out. Well, I chose x equals 10 because our number system that we primarily use, is a base 10 number system, meaning that each digit, right, each place in a particular number is a power of 10. The first place, the singles, is actually 10 to the 0 because 10 to the 0 is equal to 1. But then once we go to the next place, it's 10 to the first, and then after that, 10 to the second, after that, 10 to the third, right? Hundreds are 10 to the second, thousands are 10 to the third, 10,000s are 10 to the fourth, 100,000s are 10 to the fifth, millions are 10 to the sixth, etc. So in other words, right, when I have something like this, and I've got 2 times 10 to the third, plus 5 times 10 to the second, plus, maybe I'll put that 2 out here just to be consistent, times 3 times 10, let's say to the first, plus 4, well, then I've got 2,000 plus 500 plus 30 plus 4, and I've got 2,534. All right. Now, if x wasn't equal to 10, this would be a whole different ballgame, right? But the idea is that 2x cubed plus 5x squared plus 3x plus 4 is sort of analogous to the number 2,534, because what 2,534 is 2 times 10 to the third plus 5 times 10 to the second plus 3 times 10 to the first plus 4 kind of times 10 to the 0, if you will. Now, that's not really the thrust of our lesson today. What we're going to be looking at today is primarily multiplying binomials. Now, we previously saw how to multiply polynomials by monomials. In this lesson, we will review multiplying polynomials by each other. The key is the distributive property. And we're going to begin by looking at the product of two binomials, right? Two polynomials that simply have two terms each, and that is probably the most common type of multiplication of polynomials that you see out there. So let's take a look at exercise number 2. Consider the product of 3x plus 2 with 2x plus 5. Letter A, find this product using the distributive property twice or possibly with FOIL. All right, and we'll kind of talk about both of those in just a moment. But let's first just write the product down. All right, so in other words, I'm trying to figure out what 3x plus 2 times 2x plus 5 is. Now, we can use what's known as the distributive property twice, and we can kind of think of the 3x plus 2 as a single quantity. The idea being that this would be 3x plus 2 times 2x plus 3x plus 2 times 5. This is what's known as double distribution. This is the first distribution. And then the second distribution is, we're going to go in this direction. 2x times 3x is 6x squared. 2x times 2 is 4x. 5 times 3x is 15x. And 5 times 2 is 10. Then traditionally what we do is we combine like terms. Now the only like terms here are the 4x and the 15x. And when we combine those together, we get 6x squared plus 19x plus 10. All right. Now, before we move on and take a look at an area model, let's talk about this FOIL method, because that's often how teachers teach to multiply two binomials together. Some teachers hate it. I actually kind of like it because it allows me to quickly multiply two binomials without doing all of this. So real quick, let's take a look at the FOIL method. I'm going to have to extend my page a little bit, but that's okay. Right? So the FOIL method, first, outer, inner, last. All right, 3x plus 2 times 2x plus 5, right? The FOIL method says that we should do the following. We should multiply the first two terms together, 6x squared. We should multiply the outer two terms together, 15x. We should multiply the inner two terms together, 4x. And we should multiply the last terms together, 10. And then, of course, we combine like terms and we end up with that final answer. All right, foiling is a very quick way to be able to get to this step without having to write down this step first. And essentially it boils down to this. Every term within one parenthesis must multiply every term within the other parentheses. So if you have two terms here times two terms here, you're going to ultimately have four terms in this particular part of the product, and then two of those things are going to combine. Let's take a look at how we can represent this product using what's called an area model, which will be very helpful when we have more complex products. Letter B. Represent this product on the area model shown below. All right, so the idea is, let's say we have a rectangle, and one side has a length of 3x plus 2, and the other side has a length of 2x plus 5. We can break that up as a length of 3x plus a length of 2, and a length of 2x plus a length of 5, and then we can just multiply each portion. So 2x times 3x would give us an area in this particular rectangle of 6x squared. 2x times 2 would give us an area here of 4x. 3x times 5 would give us an area here of 15x. And 5 times 2 would give us an area of 10. Then the idea is that we should combine all these areas together to get our final polynomial. Now, the only two that can actually combine are these two along the diagonal. And that allows us to then say that our final answer is 6x squared. Combining those two together gives us 19x, and then plus 10. Now, I would suggest that if you're multiplying two binomials together, you use the FOIL method because it's fast, it's relatively easy, it allows you to understand where all three sort of portions of our final answer come from. But the area model works great. You know, if this works well for you, do it. It helps you keep in mind and keep track of all the different products that are going into multiplying the two polynomials together. Let's go on and take a look at maybe more complex issues. Exercise number 3. Find the product of the binomial 4x plus 3 with the trinomial 2x squared minus 5x minus 3. Represent and evaluate your product using an area model. Even though the result has an x cubed term in it, the area model can still help us to keep track of the product to make sure we are distributing correctly. So again, I would probably almost never myself use an area model to multiply a binomial by a binomial. But when I have a binomial times a trinomial, now that's helpful. Let's see how we can do that in this particular problem. All right, so what I'm going to now do is, instead of having a 2 by 2, I'm going to have a 2 by 3. So I'm going to break this thing up kind of like this. All right, along this side, I'm going to have 4x and positive 3. And along this side, I'm going to have 2x squared. Keep the signs with the terms, minus 5x and minus 3. All right. Now, we could definitely do this again with double distribution or triple distribution, depending on how you want to look at it. But look at how easy this is going to be. So I'm going to take this trinomial, and I'm going to multiply each term by 4x. So 4x times 2x squared will be 8x cubed. 4x times negative 5x will be negative 20x squared. And 4x times negative 3 will be negative 12x. Now I'm going to do the same with the positive 3. 3 times 2x squared is going to be 6x squared. 3 times negative 5x is going to be negative 15x. And 3 times negative 3 is going to be negative 9. The beautiful thing is, just like before, what we can now see is that all of our like terms are along the diagonal. Let me do this with a different color just so that we can really kind of hone in on this. Right? Those like terms are along the diagonal, which makes it very visually easy to see how we combine them. Now we'll go back to blue. All right, so nothing is going to combine with our 8x cubed. But then we have positive 6x squared and negative 20x squared, which is going to net us a negative 14x squared. We have negative 15 and negative 12, which is going to be negative 27x to the first. And then nothing's going to combine with that negative 9. All right, so simple enough with an area model. And again, you could definitely multiply these without an area model. You could first multiply everything by 4x, then multiply everything by positive 3, right? Distribute the 4x and the 3 both to this trinomial and then combine like terms. I love the area model though because those like terms always end up being along the diagonal. Very, very nice. All right, so let's get back to this idea of equivalent expressions. Now, it's critical to understand that when we multiply two polynomials, our result is equivalent to this product, and this equivalence can be tested. All right, and again, it's important. We're multiplying polynomials almost always for a reason, to solve a particular problem for a particular reason. But we always want to make sure that we understand that when we multiply two binomials and we get, let's say, a trinomial, that trinomial and the product of the two binomials are equivalent. Let's take a look at that issue in exercise number 4. Consider the product of x minus 2 and 2x minus 5. Evaluate this product for x equals 4. Show the work that leads to your answer. All right, so in this case, all I'm doing, and let's do this together, it's easy enough, just purely numerical work. All right, I'm just putting in 4 wherever there's an x, which is a little bit more complicated in the second portion, and I just want to see what that product's equal to. So 4 minus 2 is equal to 2. 2 times 4 is 8 minus 5. So then we'll get 2 times 3, and we'll get 6. All right, great, right? So in other words, if I take x equals 4, and I substitute it into both of these two expressions, and I find their product, I get a product of 6. Now let's take a look at letter B. Find a trinomial that represents the product of these two binomials. In other words, I'd like you to multiply these two out. I'd like you to do this on your own. Multiply these two out and get a standard trinomial as the answer. Don't worry about x equals 4. That has nothing to do with letter B. Pause the video now and take a few minutes to do that. All right, you could use an area model, you could use double distribution, you could use foiling. Whatever floats your boat, as we say. So I'm going to do x minus 2 times 2x minus 5. I'm going to stick with foiling. I have x times 2x, which is 2x squared. I'm going to have x times negative 5, that's negative 5x. I'm going to have negative 2 times positive 2x, that's negative 4x. And I'm going to have negative 2 times negative 5, be careful there, that's positive 10. So all of this is going to be 2x squared minus 9x plus 10. All right, simple enough, should be easy. Now let's take a look at letter C. Evaluate the trinomial for x equals 4. Verify that it has the same value as a. So in other words, right, if this is truly the correct product of those two binomials, that when I put x equals 4 in here and I evaluate what it gives me, I should get 6 as well. So without your calculator, pause the video now, substitute x equals 4 into that trinomial, and see if you get 6 as well. Pause the video now. All right, well, let's do it. Here we go. 2 times 4 squared minus 9 times 4 plus 10. That's going to be 2 times 16 minus 9 times 4 plus 10. 2 times 16 is 32. 9 times 4 is 36 plus 10. 32 minus 36 is negative 4 plus, plus 4, I don't think so, plus 10, and that gives me 6. And that is what I should have gotten. Because again, the idea is, right, that this product and this trinomial are equivalent. So if I plug something in here and I get a particular answer, and I plug the same number in here, I should get the same answer. Now let's take a look at letter D real quick. All right. What is the value of the trinomial when x is equal to 2? Can you explain why this makes sense based on the two binomials? All right, so what I'd like you to do is I'd like you to take x equals 2 and substitute it into this trinomial and see what you get. All right, well, let's do it. All right, here I'm going to have 2 times 2 squared minus 9 times 2 plus 10. All right, I have 2 times 4 minus 9 times 2 plus 10. I'm going to have 8 minus 18 plus 10. 8 minus 18 is negative 10 plus 10, and I get 0. All right, so x equals 2 is a 0 of this expression. Now, the second part of this is, can you explain why this makes sense based on the two binomials? So why is it that based on these two binomials, x equals 2 should be a 0 of this trinomial? Take a moment and think about this. Well, right, keep in mind that this trinomial and this product are equivalent. So if I take a look at the original product, right, x minus 2 times 2x minus 5, let me extend the page a little, extend the page a little bit, try to extend the page, there we go. Right, if I put x equals 2 in here, I'll get 2 minus 2 times 2 minus 5, right, and I'll get 0 times 4 minus 5, which is 0 times negative 1. Now, it doesn't matter so much the negative 1. What matters is the fact that this particular factor is equal to 0 when x is equal to 2, right? And so this is equal to 0. So why does it make sense that the trinomial would have a value of 0 when x is equal to 2? Because one of the factors is equal to 0. And anytime a factor is equal to 0, then the product will be equal to 0, right? A factor is simply part of a product. And if one part of the product is equal to 0, it's all equal to 0. Like if I said, what is the product of 10 times 3 times negative 8 times 0 times 5 times 15? It's 0. Because one of those numbers in that list that we were doing the product of was equal to 0. If you have 0 of something, or you have a whole bunch of zeros, then what you have at the end of the day is 0. Let's keep working with that idea. Now let's take a look at the product of 3 binomials. Exercise number 5. The product of 3 binomials, just like the product of 2, can be found with repeated applications of the distributive property. Letter A. Find the product x minus 2 times x plus 4 times x minus 7, express in standard form. Use area models to help keep track of the product. Now keep in mind, right, just for a moment, forget about this product. Let's say I asked you to find the product of 3 times 5 times 2. All right, just for a moment, entertain the thought that I'm not asking you to find the product of 3 binomials, but just 3 numbers. Well, if you're finding the product of 3 numbers, you can find the product of any 2 of the numbers, get that answer, and then take that answer and multiply it by the third number. So for instance, I could do 3 times 5 and get 15, and then times 2 and get 30. Or I could do 5 times 2 and get 10, and then multiply by 3 and get 30. Or I could do 3 times 2 and get 6 and multiply by 5 and get 30. By the way, there I'm using the associative and commutative properties of multiplication. And the same thing is true here. I can take any two of these, multiply them together using FOIL or area or whatever, get a trinomial, and then multiply it by the last one. So, or by the third one that I didn't get involved in the product. So let's do it. Let's just find this product. Let's figure out what x minus 2 times x plus 4 is, right? That's going to be x times x squared, 4 times x plus 4x, negative 2 times x, negative 2x, negative 2 times 4, negative 8. So that's going to be x squared plus 2x minus 8. All right. So that's no different than like when I had those three numbers that I erased. Finding the product of two of them. That's the product of the first two. Now what I want to do is take that product and multiply it by x minus 7. And this is where I like using an area model, because I think it's easiest now to take something like this and go x minus 7, x squared, 2x minus 8, and now let's just do it together. We've got x times x squared, which is x cubed, 2x times x, which is 2x squared, negative 8 times x is negative 8x, negative 7 times x squared is negative 7x squared, negative 7 times 2x is negative 14x, and negative 7 times negative 8 is positive 56. I can now combine like terms. Nothing combines with my x cubed. Negative 7x squared, positive 2x squared is negative 5x squared. Negative 14x and negative 8x is negative 22x. And nothing combines with the 56. So that's it. X cubed minus 5x squared minus 22x plus 56. The remarkable thing, of course, is just like that example where I just had the three numbers. If you had said, well, I really want to do x plus 4 times x minus 7 first, get a trinomial and then multiply by x minus 2, you would still get this. Or if you did x minus 2 times x minus 7, got a trinomial and then multiplied by x plus 4, you would still get this. Doesn't matter which two you multiply first. All right. Now, letter B. Based on its factored form, for what three values of x will the cubic polynomial that you found in part A have a value of 0? What famous law is this known as? So in other words, what we talked about in the last problem was that if any one of these three factors is equal to 0, then the entire product would equal 0. All right? What three values of x will make that true? Pause the video now and see if you can figure that out. All right, well, to make x minus 2 equal to 0, x would be equal to 2. X plus 4 would be equal to 0 when x is equal to negative 4. And x minus 7 would be equal to 0 when x is equal to 7. So any one of these three, right, should be zeros of this polynomial. Because, right, this product and this polynomial are equivalent, and any one of these three, if you substituted them into this product, would make one number in the product equal to 0, which would make the entire product equal to 0. Now, what famous law is this known as? This is known as, appropriately enough, the zero product law. The zero product law states that if any part of a product is equal to 0, then the entire product is equal to 0. Or a product will be equal to 0 if any one part of the product is equal to 0. All right? And we use this actually a lot when we solve polynomial equations that are set equal to 0. Remember when you were solving all these quadratic equations equal to 0? And you did actually do that just a little bit in geometry when you solved systems of equations, all right? But you'd get the equation equal to 0, you'd factor it, so it kind of looked something like this, then you'd set each factor equal to 0, and you'd solve the zero product law. Very, very important. But let's verify this. Now, letter C says test one of the three values you found in B to verify that it's a 0 of the cubic polynomial. All right, so here I've got my cubic polynomial. All right, that magically just appeared when I touched the board. All right, and I want to test one of these, and I'd kind of like to test it without my calculator. So I think I'm going to avoid the -4 and the 7, and I'm going to test x equals 2 in it. All right, so let's take a look, right? So if I test x equals 2, all right, I'll get 2 to the third minus 5 times 2 to the second minus 22 times 2 plus 56. So I'm just testing this polynomial when x is equal to 2. 2 to the third is 2 times 2 times 2, which is 8. 5 times 4. I'll just leave this product as it is right now. We'll get to it, I promise. Okay, so we then have 8 minus 20 minus 44 plus 56. Now I can do a little rearranging. I can say that's 8 plus 56 minus 20 plus 44. And let me extend the page a little bit. 8 plus 56 is 64. 20 plus 44 is 64. And that is in fact a 0. All right, and it's kind of amazing, right? The fact that, it's easy to see why when you put x equals 2 into this product, you'd get 0 times 6 times -5. That's simple to see why that would be equal to 0. It's a lot less obvious that when you plug x equals 2 into this thing, it's going to be equal to 0, and yet it is because this polynomial is equivalent to this particular product. And if I put -4 in, it would be a lot uglier, and 7 in, also kind of uglier just because there's bigger numbers, but I would also find that those two were also zeros of this expression. All right, let's wrap this up. Multiplying polynomials is something that we certainly will do quite a bit of in Algebra 2, especially in later units. We'll also use this very important idea of the zero product law in order to solve polynomial equations and find zeros of both expressions and the zeros of functions that we graph in the coordinate plane. For now, I'd like you to get some real practice on tonight's homework on both multiplying polynomials and on the zero product law, because they are both critically important ideas as we move forward. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.